changes its reactivity. And so if we don't have any acids, so for example, oxygen without acid, without the H plus, will it form dihydrogen monoxide? Well, oxygen without the H plus will form hydroxide. What's more stable, hydroxide or water? Water is a lot more stable. And so if there's no acid present, then what happens is the rank here drops significantly. So this is at plus 0.401. But if we look at oxygen,
but why does it go between those two? Because I see the number 1.246 goes between.
no, it's this one, minus 0.828.
Oh.
Minus 0.828 fits between here. Oh, zinc, sorry. It's between zinc and iron, too. Am I reading this? No, it's between zinc and aluminum, right? You see that? That's right.
But it's not there because it needs the acid?
Well, this is for basics. So actually, this acid and base step, don't worry about it. We'll just rank it there.
Okay.
Just make it one table. If you look at the chart in our room, the chart in our room has everything together. This chart decided to split it up, but take a look at the chart in our room. Okay, so we get familiar with the chart. And this is the method. This method is the same as the Bronsted acid base. It's just the chart is more difficult to use. And so we inventory the species. Well, we had to inventory the species for Bronsted. And then we find the strongest oxidizer. Well, we had to find the strongest acid. How did we find the strongest acid? We looked at the chart. Well, how do we find the strongest oxidizer? We look at the chart. And so technically, this method, you don't need to know any chemistry to use this. It's just steps. Can you follow the steps? That's it. And so you probably could train even an elementary school child to do this just by telling them where to look on the chart and how to use that chart. But so we don't need to know what makes a strong oxidizer. We don't need to know what makes a strong reducer. We just have to find it on the chart. Finding it on the chart, well, that poses a problem because some people never look at the chart and they see that some things can be both, an oxidizer and a reducer. But anyway, we combine the strongest oxidizer with the strongest reducer, and then essentially it's very similar. This method is going to yield the NIE, net ionic equation, so we don't have to worry about doing the complete, the ionic, and the net ionic. Okay, there's other cases where it fails. The single replacement method failed. Copper and nitric acid. Copper and nitric acid single replacement is going to fail because nitric acid is what we call a what? Well, you can look it up there, but copper and nitric acid is going to form copper 1 or copper 2 nitrate? Copper 2 nitrate. And not H plus, H2 gas. Okay, then we'll balance it like this. Then we look for driving force. And so what we compare is compare the activity of copper versus hydrogen. It turns out that this is less active based on this chart, and this is more active. And so what we get is we get no driving force. And therefore, if there's no driving force, we say that there's no reaction. But we have to remember that we're only looking at single replacement. Single replacement is narrowly defined. Well, that turns out to be wrong. This is wrong. There is reaction. And we have to use the chart method. To determine it.
Can we back to the chart?
Okay. If we go back to the chart, we see that hydrogen is more active than copper. Hydrogen is closer to lithium. Sorry, see. All right, so what we're going to do is we're going to do this next one. So just in an effort to save some time here, I'm going to do potassium is carefully added to sodium chloride solution. So if we do potassium solid goes to and sodium chloride, then there shouldn't be any problem because potassium is a pretty good reducer, right?
Yeah. Yes.
And then chloride is not a good oxidizer, but sodium ion is okay.
Mm-hmm.
And so what should this form? This should form KCl and sodium. Okay, then let's compare sodium and potassium. Which one is more active, sodium or potassium? Which one's closer to lithium? Potassium. Potassium's more active. And so we say potassium, this is more active. This is less active. Therefore, driving force, right? But this is wrong. This is wrong. Uh-huh. Was there a question?
So you should do two methods to prove.
No, I don't bother. Or I know. Because I know all the exceptions.
Like that one, we did it regular and it was wrong. So
Yeah,
we had
this
to
is
use
wrong.
The chart method, but then that one we used the chart method and it's wrong. So then.
No, we didn't use the chart method. This is not the chart method. This is single replacement. The single replacement, this is wrong.
Can we use the chart method?
Yeah, so this is wrong. Must use chart method. So even though this seems like it should work, and it gave us a driving force, it didn't work. This one didn't work. It didn't work because there's a more powerful oxidizer than sodium ion. What's a more powerful oxidizer than sodium ion?
Potassium.
Well, all these, anything above this is more powerful. Potassium's worse. Potassium ion. And so all these above here, well, there is one other species that we're ignoring, or that we forgot. What's the one species that we've forgotten? So let's just do this one here. Let's do this one as a quick example. Of using the chart method. Okay, so what we have here is we have potassium solid metal plus sodium chloride solution, NaClAq. And so let's go ahead and inventory it. Potassium metal is just potassium metal, right? It's not potassium ion. And then sodium chloride consists of sodium ions and chloride ions. And then there's one more species. What's the one more species? There's water. And so we look at the chart. So let's consult the chart. What is potassium? Potassium is on the reducing agent side. So we say potassium is a reducing agent. What is sodium ion? That's on the fluorine side. If it's on the fluorine side, it's a oxidizing agent. Some species occur on both sides. So they're both a reducing agent on the lithium side or an oxidizing agent on the fluorine side. They occur on both sides. You can find which species there are if you read the chart. Chloride is just on the lithium side, so that's a reducing agent. Water is on both sides. Water is both an oxidizing agent and a reducing agent. Okay, then what we do is we pick the strongest reducing agent and the strongest oxidizing agent. So let's pick the strongest oxidizing agent. What is the strongest oxidizing agent on the chart? Fluorine. Fluorine. Well, we don't have fluorine. So what do we have? We have sodium ion and water. And so let's go down the chart. Oh, yeah, I see. Here's sodium ion. Here's water. So sodium ion's stronger than water. Right? No, wrong. Because water is misplaced. Water belongs. Yeah, and so water is a stronger oxidizing agent than sodium ion. And so the single replacement method failed because it didn't even take into account water. And so water is the strongest oxidizing agent present, and we're good. Now let's go to the reducing agents. What's the most powerful reducing agent? Lithium. And so let's figure out. We have it's between potassium, chloride, and water. Well, here, yeah, if you look at it, potassium is going to be the strongest. Right? This is the second strongest.
So for reducing, you go down, and for oxidizing, you go up.
No. Don't think in terms of down, up, always, because it depends. The problem is sometimes the chart is flipped upside down. If the chart is flipped upside down, which it is in your book, then you go towards lithium, as the strongest, and you go towards fluorine, which would be the strongest. And so you use lithium. It doesn't matter if you're upside down or right side up. You just look for lithium and you look for fluorine, and then you can get your bearing. You can be sideways. And you go left or right, it doesn't matter. You look for lithium and you look for fluorine. Then you can figure out which way to go. Okay, so now what we see is, okay, potassium, and then where is chloride? And where's water? Is this water here? No. In fact, water is way up there. So what's better, chloride or water? Let's just take a quick look. Chloride's one of the worst. It doesn't want to lose electrons. Chloride's here. And if you look at water, water is pretty bad, too. Chloride and water, they're pretty bad. And so the strongest R is potassium. And so what we do now is we just copy the reactions. So for example, chloride, actually we're not doing chloride. For example, water. Water is the strongest oxidizing agent. And so we copy this reaction down. And so what I'm going to do is I'm going to copy that. I'm going to copy 2 H2O, liquid plus 2 electrons yields H2 gas plus 2 hydroxide. Okay, then I go to potassium and I copy that. But when I do potassium, I have to go backwards here. I have to reverse this. In other words, flip it, because potassium is not a product. Potassium is a reactant. And so what I'm going to do is I'm just going to flip that reaction around and go potassium solid goes to potassium plus an electron. And so now I have my 2 reactants, water and potassium. This chart, we have to flip one to use it. And so one gains electrons, the other loses electrons. Well, when you look at this one gains how many electrons?
2.
This one loses
1.
It's a mismatch. So what we have to do is we have to match it by multiplying the entire equation.
To know the difference which water to use, it's just like you just have to look at the
You use the strongest water. The strongest. If you have a choice of 2 waters, pick the stronger one. Which one's stronger? The one that's closer to lithium or the one that's closer to fluorine?
Okay.
You pick that. Well, it depends. If water can go either way. It can be an oxidizer or it could be a reducer. Okay. All right, so now we just multiply the entire thing. So what we're going to get is we're going to get 2 water liquids plus 2 potassium solids. This is going to yield H2 gas plus 2 hydroxides plus 2 potassium plus. The 2 electrons cancel. And they need to cancel because we don't have free electrons. And so then we look for driving force. And so let me finish off with the driving force here. The driving force is going to go from stronger to weaker. And so this is our oxidizer here. This is our reducer here. Now, there's a conjugate relationship. So if we reverse this reaction, this would be our reducer. Because going backwards here, we lose electrons. Going forward, we gain electrons. So losing electrons is reducer. Going backwards here, we gain electrons. So this is our oxidizer. And so what we're doing is we're comparing the two oxidizers, water versus the other oxidizer, potassium ion. And then we're comparing the two reducers. The two reducers would be potassium and hydrogen hydroxide, hydrogen gas and hydroxide. That would be our reducer. And so let's just compare the two oxidizers. Which one's a more powerful oxidizer? Potassium ion or water? Water. And so this goes from stronger to weaker. If that's the case, the reducing agents must follow. And so this is a stronger, this is a weaker, and we confirm it. And so there's driving force. So this is the reaction that occurs. So a reaction actually occurs. The single replacement, you have two choices. One, you can memorize all the exceptions of the single replacement, which is a lot, or you could just learn the chart method. So the easiest is just learn the chart method. Okay, we'll stop here. We're going to take a break and then we'll start the lab. I'll talk about the lab next.